Okay, so today we're looking at similar figures. So what a similar figure is when you have the two things that are of the same shape. So say for example, if I had this square here, and so I've got a square and I might say that it's got 2 centimeters long. What I can say is, even though I've got another shape here, and we're saying this one's 5 centimeters, maybe 5 centimeters length, it's a similar figure. So what makes a similar figure is that often their ratio, their angles are the same. So if you look at it, they all have this one, it's all 90, each of them have a 90 degrees angle at each corner when you have a square. And what happens if they're similar figures, it means the ratio of their sides are the same. And what that means is, so say for example, we've got this square and we say 2 centimeters. So say I was looking at this side length down here. So if I said, all right, compared to that one, so I'd say I've got the bigger one. So we say it's 5/2. That's when you have a ratio. So this one is 5/2. But if I did the other side, say I did this side where I know that's 2 and that's 5, that would be the same, wouldn't it? 5/2. So see, it's the same fraction, yes? So that means their sides have been blown up the same way, so or enlarged. It can also go the other way. You might have shrunk them in the same way. That means that they're similar figures. So you could have say for example, you could have a triangle and it could be different. So say we could say this is 3 and that's a side. I'll make it an isosceles. And then I might have a bigger one where I have 6 along there and I've got 4. All right, if I compared their sides, so say, here, so I'm looking at this side over that side. So that would be 6/3, which would simplify down to what? 2? Yep, so would you agree that this side here is 2 times larger than that side? Yeah. Now, if you compare the other two sides, 4/2, does that go down to 2 too? Yeah? So really so can you see the sides were enlarged by the same amount or the same ratio, we say? Yeah? That's when we know we have similar figures. All right? So what we call that, if you look here, what we were talking about here where I said, it enlarged when we went from here to here, it went up by a scale of 2, wasn't it? The bigger one is 2 times bigger than the other one. What we call that is the scale factor. So that means how much it has changed from that. We'll say this was the old object and this is the new object. So we can calculate the scale factor. So that's what I did before. I said, all right, the new object had a 6, and then if I looked at the same side, it had a 3. So I saw that the scale factor was 2. Okay? So if they said the ratio was 1/3, we'll draw a little example down here. So we would have, if I did a square and I said it was 1 centimeter and we had a 1/3, then this big square, if they were similar, that would have a 3 centimeters. Yeah? We can say it like that, 1/3. All right. Let's go look here, and we've got couple of examples of similar figures. So a circle, we could say they're similar. And over here, we can say 2 squares can be similar. So if over here, we're going to look down at the next one, down here. We're going to see if it's similar. So if these two numbers were similar, we would get the same ratio or scale. So I'm going to call this the old object and this is the new object. So if I do this side here, say I was going to try and work out the scale factor. So I go 8/4, that would equal 2. So that means if it's similar, we should get the same value when we do the other side. So if I'm going to do the purple side, but that's 1/1, which is 1. So this is why this one is not similar. See, because the ratios, they didn't enlarge up the same way. So if it's enlarging up the same way, they all have, every side had to go up by the same amount. Okay, so here we can see with this one, this bottom one is similar, because 8/4 would give what? 8/4 gives 2, and then if you do the other one, 2/1 is 2, so they're the same. Okay, so they enlarged by the same amount, so this one is similar.
So just divide the old by the new.
Yeah, pretty much, to find the scale factor. We'll just go over that. So someone just asked then whether the large one is always on top. Not necessarily. So if I did I'll do another example of similar figures. So what you could do is you could have, we could say, I'll draw a circle this time. We could have this circle with a diameter of, say, 6 centimeters. And then what we did is we went, and then our next one was, has a diameter of, say, 1 centimeter. So what we're saying, we're going to call this the old object and what it went to be the new. So these are similar because all the angles are the same. It's a circle. And you can just compare because they're both giving us the diameter, so we can compare them. So if we were looking at the scale factor here, we would say scale factor equals new over old. So it would be 1/6. So the new object is 1/6 of the original. So doesn't necessarily have to be. You just have to look at what they say, which way it's going. So here in our question down here, it says the rectangles are shown to be similar. So they often will tell you that they are similar, so you know you can do this process. And it says in part A, it says find the ratio of their side lengths. So all you have to do there is compare the same sides. So here we're going to take the long side and we're going to compare it over the short side. So we'll say, we'll go new over old if you like. And if you look, it would be 25/5, which can simplify down to, we can just say 5/1. So you could write it like that. You could say it's 5, or if they say a ratio, we'll say 5, it's 5:1. Okay, and then you want to compare the other side. So the other side was 10/2. So that ends up being 5/1. So they're 5/1. So we've definitely proved these numbers, these shapes are similar. Now, if they, it says find the ratio of their areas. So we've done a little bit of area work. So first of all, let's find the area of these two rectangles. And what's the formula for area of a rectangle? Length times width, yeah? So it will be 5 times 2. So this one is 10 centimeters squared. And if we do this one, it would be 25 times 10, which equals 250 centimeters squared. Okay, so they've asked me to find the ratio of their area. So the ratio of their area, so all you have to do is we'll put the new over the old again, but we'll use their area value. So we'll do 250/10. Now we can simplify that to be 25/1. And we could write it as a ratio as 25:1. All right, so if you're looking at that, what do you notice? What we want to see is, if you notice the length, what we call this up here when we're just comparing the side lengths, we often call this the length ratio. So when we compare sides, that's called the length ratio. And then obviously when we compare areas, that's called the area ratio. Now, can you see in this instant, the length ratio was 5 and the area ratio was 25. So how much times bigger was the area in like scale factor? 5. And if you look at the number 5, what's 5 squared? 5 times 5 is 25. So what you actually know, if you know the length ratio, and we're going to see this in a minute, you can work out the length ratio. So say you know the length ratio, or we say the scale factor, we say K, we can work out the area ratio by squaring that value. So because it was 5 over 1, we could say the area was 5 squared, so we know it's 25. We'll do some practice, don't worry, but this is how it was going. Okay, so what we've got 2 shapes shown as similar. So they've told me they're similar, so I don't have to prove it. We know, okay? So it says, determine whether the shape has been scaled up or down and give the second shape and find the scale factor. So what they're saying is they're going from this way to this way, okay? So we just call that the old and that the new. And when we go to work it out, it says they want us to find the scale factor. So often scale factor, they use the letter K. So if you see K, it just means they want you to find the scale factor. And we know that means the new, now that's the new over the old. So here, we just got to make sure we pick the same side. So we're going to go say, we're going to pick this side, and I'm going to say the new had a 2 and the old had a 3. So the scale factor is 2 over 3. All right, now they've asked me here, they've said, what is the scale factor for area? So just to do this part, we're going to do like what I said before. I said before, if you want to go from the length ratio to the area ratio, remember if we've got a K value here, we just square the K value over here. So in this example, you've already worked out the length ratio. It was 2 over 3. So to get the area, all you have to do is you square both numbers though. You square both numbers. So what is 2 squared? 2 times 2 is 4. And what's 3 squared, which would be 3 times 3? 9. Okay, so the area of the new shape is the 4/9 smaller than the original. So we did go smaller, didn't we? So we're going to have a smaller number. So if you were writing the answer for that, because they said get the scale factor for the areas, you just write 4 over 9, okay? Okay, so let's have a look. They've told me that the triangles are similar. So you get told they're similar, and that's a trick to know that you're doing one of these questions, because they'll tell you that. Now, if they say find the value of x, so here they've asked you to find the value of x. So when you know they're similar, remember when before we said if we compared the two sides, so if I call this one the old image and this one the new image, remember when we compared the two sides, they ended up giving the same number, didn't they? Because they're similar. So what we're saying is that if you compared these two sides, if I said 10 over 24, so those two sides, so 10 over 24, so remember new over old, because they're similar, it should equal the same as if I said x over 18, yeah? Because we said they're similar, they should produce the same amount. So you can just write, as soon as you write out that, if you have an equation with an equal sign and you've only got one letter, you can use your solve function. And let's just use that. We don't need to rearrange it. Let's just use our solve function and find it on our calculator. So so we got x to equal 7.5 centimeters. Okay, and it should be, have a think about it, it should be smaller than the old image, shouldn't it? Because it's shrunk, yeah? So the old image says it's 18, so 7.5, so we know we're like correct. Okay, so a map on a scale has, a map has a scale of 1 to 20,000 written on it. If the measurement on the map if the measurement on the map between the two towns is 5.4 centimeters, what's the actual distance between these two towns? And give your answers in kilometers. So correct to 2 decimal places. So when you see this written on a map, okay, what that actually means is, so we've got this 1 to 20,000. What that means is this is on the map and this is real life. So whatever you measure on the map, so say for example, 1 centimeter on the map equals 20,000 centimeters in real life. Okay, does that make sense? Yeah? So you know that 1 centimeter is 20,000 centimeters. So if on this map we've got here, they've said, all right, the towns are on the map. The map, it says it equals 5.4 centimeters. What we're going to do is, well, 1 centimeter is 20,000. So if we times this by 20,000, we're going to know how many centimeters it is in real life. So in real life, it's 108,000, and that's centimeters, okay? But we want to get into kilometers. So let's divide, if we divide it by 100, that would give us meters, and what would that be? So you divide by 100, you've got 1,080 meters. Is that true? Yeah. And then if you want to get it into kilometers, we could divide by 1,000. Isn't there 1,000 meters in a kilometer? Yeah. So we get 1.08 kilometers between the two towns. It's pretty close.